My name is Hayden Bliss. I'm the Director of Sales and Marketing here at Biomark. And I want to thank you all for attending this morning. We hope that you and your loved ones are safe and healthy at this time. And today's webinar is going to highlight a project that Biomark has been working on for over 10 years now. And shortly I'll introduce Steve Angley, our Director of Technical Services here at Biomark, who has been heavily involved in this project as well for many years. And he'll be presenting this today. Before we get started though, a few housekeeping items. As also mentioned in the chat, everyone's on listen-only mode. We do this so we don't have any microphone issues, feedback, screaming children, barking dogs, those sort of things that some of us have experienced while we're working remotely. We encourage you to ask questions and comments during the webinar. Those will show up in the right-hand side of your screen here, so you can type those in. You can do the Q&A section, message us directly. And as those come in, I'll jump in and ask those questions to Steve so he can answer them in real time. We'll also record this webinar, so you'll receive a link afterwards, and it'll be on the website. We'll post it on social media, so feel free to share it with anybody you want. So stay on the call afterwards for a few minutes if anybody has any additional questions, comments. So please feel free to join us if you would like. But once again, thank you everyone for taking time to join us today. We really appreciate it. And with that, I will turn it over to Steve.
All right. Thank you, Hayden. As Hayden mentioned, I'm the Director of Technical Services here at Biomark. I've been with Biomark for almost 18 years, and it's been exciting and fun to work with customers developing RFID monitoring solutions for a variety of applications, from small in-stream systems to assisting in the development and management of the project that I'm going to speak about today. So thank you for joining, and let's get on with it. Get to the right screen. So first I want to recognize co-authors Alex Artsikoff, who's a senior electronic engineer here at Biomark, Yuri Smirnov, who was our fellow electronic technician electronic engineer that developed a lot of the antenna and reader technology, and then also Gabriel Brooks, an electronic technician for NOAA Fisheries. And the presentation describes almost a 15-year project that involved multiple federal, private entities, as well as many entities within those organizations. I'm going to go over the basic structure of the presentation, kind of give you a description of the passage routes that are present at the dams in the Pacific Northwest, go over the phases of development of this project, and then ultimately the installation at Lower Granite Dam. The study area for the project is in the Pacific Northwest of the United States, predominantly in the Columbia River Basin. The areas of interest are the Lower Snake River, which is here, consists of 4 hydroelectric projects, and the Lower Columbia River. The projects of particular interest, or the dams of interest, are Lower Granite Dam, which is the first hydroelectric facility encountered by juvenile salmonids migrating downstream, and then Bonneville Dam, which is the last project encountered by juvenile salmonids. All of these locations have adult and juvenile passage structures, and all of those structures have pit tag detection in them. Detections at the locations are transmitted automatically to a regional database called the Pit Tag Information System, or PTAGIS. So it's a very extensively wired array within the main stem, as well as many tributaries in the basin. To give you a sense of the scale of the dams that we're talking about, this is a picture of Lower Granite Dam with a spillway in the middle of the river, and then a powerhouse on the right-hand side at this particular location. Passage, the juvenile bypass systems within the powerhouse typically consist of a guidance system that guides juvenile fish with the use of intake screens into a bypass system that then they're routed to a collection facility downstream of the dam. The other option for passing through the powerhouse is to go through turbines. Obviously, it's spill, the animals just pass through spill. There are pit tag detectors in the juvenile bypass system, but there are not the currently detection systems within the turbine passage route or the spillway. One of the impetus for this project is that as the operation and management of the hydro system has changed to emphasize spill, there are fewer fish passing through the juvenile bypass system and therefore fewer pit tagged fish. And the NOAA Fisheries, who is responsible for determining the smolt to adult return rates of those fish, is basically running out of data, or they're not getting enough pit tag detections to provide reliable estimates for the SAR rates. And that led them, or to the region, to push for the development or encourage the development of a pit tag detection system for the spillway, since the majority of the fish are passing through that route. And the system consists of not only an antenna, but the transceiver, the tag, and the antenna, kind of the three factors that go into a detection system. The criteria for that system was tag speed, like any system that we design. The estimated tag speed for this area would be 60 feet per second, or 18 milliseconds, or 18 meters per second, or 41 miles per hour. And to get an idea of really what that means, imagine, depending on what your unit of measure is, imagine that distance of 60 feet or 18 meters, and then transiting that distance in 1 second. So it's extremely fast, much faster than any typical RFID system. The detection system needed a range of 60 inches, and then it also needed to be wide enough to be able to provide 2 or 3 telegrams of the animal or of the pit tag as it passed through. So those were the criteria. Just some references. A standard tag, and you can see the bullets, but a standard tag traveling 60 feet per second needs 2 feet of activation in order to get a single telegram. This also led to the desire to develop what's called a half telegram, which requires half the amount of time to transmit its signal compared to a standard telegram. A standard telegram requires 32 milliseconds to transmit its tag signal, and a half telegram requires 16 milliseconds. So that was the challenge, and then this is the group that was assembled or collaborated on it. It's broken into really to 2 groups. There's the Bonneville Power Administration, which provided funding for the development of the electronic equipment, and under that fell NOAA Fisheries, Desperon Fearing, Biomark, and the Pacific States Marine Commission, and the U.S. Army Corps of Engineers was responsible for all the structural work and the work at the dams. The Portland District for the first phase of development, and then the Walla Walla District for the final phase. And North Bank Civil Marine was the contractor for the final installation at Lower Granite Dam.
Hey, Steve.
Yeah.
You mentioned the half telegram tag, and somebody just submitted a question regarding that. Is that something that is being used on this project?
The half telegram tag is currently not being used. The half telegram tag is a proprietary tag that manufactured by Biomark that requires our firmware, a proprietary firmware for the readers. And the Corps wanted to, I can get into the results later on, the half telegram tag functions very well, but the Corps wanted to make sure that the system performed well for the vast majority of tags that are already at large in the system. So this system and all the data I'm going to show you is really based on the standard Biomark tag.
Great, thank you.
So the project began in 2006, and the first effort was conducted at Bonneville Dam. Bonneville Dam, it's the last dam encountered by juveniles migrating downstream. So obviously, if they survived Bonneville Dam, they've made it through the hydro corridor, and they're a goodest group to assemble to create your tagged fish that made it to the ocean. The other reason that Bonneville was selected was the access to the spillway gates in a gate repair pit that I'll show you next. And the structure of the gate lent itself to the attachment of an antenna. location of interest where the antennas would be mounted is actually on the bottom of the gate. So between the gate and the jet of water that is shooting out under the gate, just to bring it home, as this is where the antenna would be placed, would be on the gate, this environment. Here's a shot of the gate repair pit at Bonneville Dam. The testing in the gate repair pit lasted about 2 weeks, and at this time, this is when Yuri Smirnov and Mark LeMay and Alex Archikov spent that time down in the hole, building the prototype and testing. The tarp is in place to prevent the water that's on the roadway deck above them from dripping on them. They also had to, the Bonneville Dam was built in the 1930s, and the gate repair pit is used to repair gates, and they were certainly concerned as well with dust from lead paint that had been used over the years. So there's a fair amount of cleaning in that environment to make it suitable to work in there. So here's the gate repair pit. That's the test subject. And then this is the leading edge, or the bottom of the gate repair pit. And the challenging aspects were the curvature of that gate. It's not just a flat wall or a sill that you could easily mount an antenna to. So it's kind of a two different radiuses that they had to deal with. And it's also metal. The metal absorbs the energy of the antenna's electromagnetic field and reduces its effectiveness. So they had to come up with a means to isolate the antenna when it's placed on metal, but still place it in close proximity to the metal. To provide the isolation, the group used ferrite tiles. See the little 4-inch by 4-inch tiles on the right to provide shielding from the gate. And the ferrite tile absorbs the energy of the electromagnetic field that's created by the coil within itself, and enhances the quality of the antenna by doing so. And for this effort, they constructed two 25-foot antennas that were end-to-end that then would be attached to the bottom of the gate. The wooden structure is the jig that they use to hold the antenna in place, but you can get an idea of where the antenna would be mounted on this bottom edge. And they also used Litz wire as opposed to a traditional copper wire to form the coil. I don't know if you haven't seen Litz wire, it almost looks like a multi-strand fiber optic cable. A wire that's rated as a 10 gauge has almost 1,000 strands. It has over 1,000 strands in it, and each of those strands is insulated. And that insulation helps reduce what's called the skin effect and reduces the interaction among the conductors, among the neighboring conductors, and provides a low resistant cable that can push a lot of current relative to a standard wire. So the effort was successful. However, they did run into some practical and logistical issues. The first one is that if you put an antenna on the bottom of the gate, you just have a single detection point. You don't have the ability to empirically determine detection efficiency. The other challenge is just mounting something to the bottom of the gate with the vibration that's occurred. They had some sensors ripped off the gate. And then with the two large 25-foot antennas and expecting thousands of fish passing through, there was a concern or realization that tag collision would be a big issue. If you have two tags that are in close proximity to each other, they would cancel out, and you won't detect either one. So those were kind of the downsides or issues, but they did learn quite a bit from the effort. They demonstrated the use of ferrite tiles to get close to the metal gate, so that was effective. Yuri updated the exciter circuit, the tag detection circuitry to be able to detect a very small tag signal out of the background noise. The transceiver was upgraded to be able to operate on 50 volts DC and push 30 amps of current to the antenna, which is significantly higher than anything that had been done before. And also, as the last bullet says, began the conversation of this half telegram tag, half telegram or fast tag. So the effort completed at Bonneville Dam The project wasn't over, but they realized we needed to go to a different location. And that effort shifted to Lower Granite Dam. And as I said, this is the first dam on the Snake River encountered by juvenile salmonids migrating down the Snake River. And the goal was to take advantage of a reshaping of the Ogee for Spillway 1 that was planned. Um, uh, and also the flow is a lot smoother. So this is lower, as I said, this is Lower Granite Dam. These are traditional undershot bays. And then the very first bay is where the antennas would be placed, and you can see the flow is quite a bit smoother in that bay due to the location of a removable spillway weir in Bay 1. The water velocity in this location could still reach up to 80 feet per second or 24 meters per second, and water depth was around, anticipated water depth was around 4 feet or 1.2 meters deep. There's a side view of Bay 1, a Lower Granite Dam, showing the RSW structure or removable spillway weir structure on the upstream side. And then this is a view from the forebay. So this whole thing can rotate down in the event of a flood. But the RSW ultimately provides a surface route for passage in a much smoother laminar flow down the Ogee compared to a traditional undershot gate. And it creates, from my previous life when I worked for the National Lab, monitoring this thing when it was developed, but it creates what's called a flow net or a river in the upper 20 feet or so of the forebay, and fish sense this flow net and use the RSW passage rate at a higher percentage than the amount of flow that's going through that location. So that was kind of advancements, and these RSWs have been since deployed at other facilities in the Lower Snake River. Just to give you an idea of what this looks like. So this is the flow underneath the gate. So this is the Spillway 1 at Lower Granite. So the idea was to place antennas on the Ogee to detect fish passing through that jet of water. Here's a section view of the Ogee. And so the idea was to place antennas on the Ogee, take advantage of relatively low flow, and the antennas would be in trenches that would be cut across the width of the Ogee. The Ogee spill bay is 50 feet wide. Each bay is 50 feet wide. And the trenches that would be cut would be 50 feet wide, not surprisingly. But they'd also need to be 7 feet deep and 6 feet wide in order to cut the rebar back, the ferrous rebar back far enough so it didn't impact the antennas, the antenna performance. Once they're placed in there. So a pretty big excavation or mining of the Ogee surface. The initial antenna design that Yuri came up with was a V-shaped antenna, and the V-shaped antenna consists of 2 independent coils. Here's a coil and here's a coil, again constructed using Litch wire. And the idea that the coils, the electromagnetic field generated by each coil would kind of push up together. Imagine a balloon or 2 balloons or 2 beach balls that you're pushing, and that interaction would enhance the height of the antenna field. The results were very successful. However, from a practical standpoint, it became unrealistic due to the fact that the angle that the antennas or the individual coils were mounted at had to be very precise, and it would be tough to manufacture, ship, and install the antennas and maintain that angle. And one way to do it was to create an antenna that encased both coils and the entire volume. So from that aspect, just this huge monolith, which would be tough to construct, install. You have a huge air void in there that can expand and contract. So even though the detection was effective from a practical standpoint, it wasn't really a buildable antenna. which then led to the use of what we call upright coils. And with the vertical antennas, we could use two or three sub antennas. In each sub antenna, this structure here, each one of those are 4 feet tall, about 8.5 feet wide, or 8.5 feet long, and then 15 inches wide. And the spacing between sub antennas could be adjusted to change the height of the field and the detection range, or we could also go down to two sub antennas as well. And in this configuration, one antenna is actually driving and the other, and then kind of pushing the field into the other coils. Let's see, and it was, the other aspect that was required was the read range. So regardless of what the antenna shaper was, we still needed to maintain this 50-inch read range above, kind of in pass-by orientation above the antenna. Here's some pictures of testing that was conducted at the NOAA Fisheries facility in Pasco. Here we have two sub-antennas that are being lowered into an aluminum tank. And to verify performance at speed, the Pacific States Marine Fisheries Commission built a pneumatic tag shuttle that would allow us, we put a tag in a wooden dowel and shoot it across the antenna at a variety of speeds and heights, starting at the top of the antenna and then moving up until it was no longer detected, and at a variety of speeds, kind of figuring out where the limit was to get adequate number of detections. From the testing in Pasco, we were able to we mapped the field using a static tag. So here's Uri. We have a test tag on a stick, and we create this shell. I think this is a graph that Gabriel put together. But we could use a static tag to determine the outer limits of detectability, and then we would also shoot like I said in the previous slide, a shuttle or a tube to determine how it did at speed. With this antenna configuration, we were able to read a tag, above 54 inches when in a static position, and that's what this orange area shows. But that area wasn't sufficiently large enough or long enough to detect the tag at speed. You had to be to detect a tag traveling at speed, 60 feet per second, that you need a length of travel that's more along the 30 inches above the antenna, so more down in here. I guess you have to assume that there's detection volume. This is the area under the shell is the detection volume. So if there's a tag anywhere under the shell, it would be detected. But it needed to be in there long enough to get the 2 or 3 telegrams, and that field was only wide enough, 30 inches above the antenna. Again, some more lessons learned. The standard tag was, we could detect that at 24 inches above the antenna when it traveled at 60 feet per second. The half telegram tag was effective at a greater distance, but then there also was an upper limit to what we were able to achieve with the half telegram tag. It wasn't detected at the 50-inch mark. So the results were good. Once again, but then it came down to kind of the structural aspect, and similar to the testing at Bonneville Dam and the Vee-Shaped Antenna, build an antenna, but building, you can design a prototype and build a prototype that's effective, but you ultimately need to figure out a way to put it at the dam. And kind of when it got to crunch time or go time in discussions with the Corps, it was determined that this 50-foot wide, 7-foot deep trench just was not going to fly. From a structural aspect, the Corps was not interested in cutting a big old notch in their forebay, which led to the shift to what we call a flat plate antenna that would be no more than 12 inches thick. So instead of having antennas that go deep into the Ogee, you would have a series of flat antennas, 1 foot tall flat antennas that would be placed in 3 different trenches along the Ogee, and as pit tag fish passed down, they would detect the fish. The speeds that were expected in this scenario were again in that 50 to 60 feet per second, and it seemed to kind of go up every time we had a discussion with the Corps. The balance between the speed and the depth of water is that the water is deeper near the top of the Ogee, and the water is slower, and then as you go down the Ogee, the water depth is lower, but the speed increases. Trying to find the sweet spot in that. This is the rendering from NOAA Fisheries, and this is the engineering drawing from the Corps of Engineers. So again, the Ogee surface. This is the end view of the location of the antennas. So there'd be 3 trenches that go across. And as I said in the beginning, for the selection of Lower Granite Dam, the Corps wanted to reshape the Ogee. You can kind of so they were going to add concrete to the surface of the Ogee to decrease the slope. And and if we built an antenna that was 1 foot tall or 1 foot thick, they would only need to excavate concrete from this upper portion of the zone where the antennas would be placed. The other 2 locations would actually allow them to put 6 inches of concrete over the top of the antennas with their planned depth without removing any additional concrete. So we have 3 rows of antennas, but there were 11 antennas in total. So here's a drawing that Gabriel put together, and you can see the 3 rows. So now we're looking in isometric or plan view. You have 4 antennas on the top row, 3 antennas in the middle, and then another 4 antennas on the bottom. And the color indicates the number of antennas that the tag would pass over. So the gray color or the gray bands indicate that the tag would pass over 2 or 3 antennas. The yellow band is a single detection or passing over a single antenna, and then the red is where there won't be detection. And if you think back to Bonneville, the issue with Bonneville is that we only had a single point of detection just underneath that gate, whereas this provides quite a bit of redundancy for detection. And also, if you think about the spill video that I showed, there's a lot of foamy water or jet of water that rides along the edge, and the assumption, maybe it was just convenient, was that there probably aren't a whole lot of fish there. So and that's only about a 6-inch strip. That's the layout of the antennas. And through significant testing, months of testing, this is the end result. So we use this is the shape of the final antennas, the final antenna design. And we use ferrite tiles, or Alex and Yuri use ferrite tiles to enhance the shape of the field, meaning like a traditional antenna, it enhances the shape of the field, meaning that it was high or almost square, like a mesa all the way across the top of the field, where a traditional antenna would have a peak in the middle and then decrease on either end or either side. And with the use of ferrite tiles, we're able to kind of push up the detection range on those far extents, and then therefore provide a much larger detection volume for each antenna. And also you can see now that orange area or volume that's above 50 inches is quite a bit larger compared to just the ridge that was present in the initial 2 or 3 vertical upright antennas. Here's a picture of the final antenna, or final flat plate antenna. Like I said before, each antenna is 8.5 feet long, 5 feet wide, and I think 11 3/4 inches thick. But then once placed in the aluminum shield, that's 1/4 inch thick. The overall height, the final height, is 1 foot tall. We built 11 of these antennas. Let's see, 11 antennas. There's a set of tuning capacitors in the antennas, and we wanted to be able to access those. So we built compartments here with a hatch to be able to change the capacitor pack or replace it if it was damaged. So at this point, we had an antenna design. We were starting to build antennas, and then the project was delayed for a year because of some other construction activities at the dam. And we utilized that year to conduct some additional testing, test the antenna performance at different cable lengths, test the antenna with different concrete mixtures, look at the synchronization of the of antennas together. So it's, this obviously is a very large scale project, and we wanted to make sure that we could test everything as much to resemble the final installation as we could, because we were going to get one shot, and we didn't want to go in and install something and find out that it didn't work, and didn't work for lack of us testing. Here's some shots, some photos of the testing. Connected synchronization testing at the NOAA Fisheries, and we synchronized the phase of all the transceivers exciter frequencies, since they were going to be on and scanning continuously. Here's Alex with some of the Biomark FS3001 transceivers. I think we tested synchronization with 7 antennas. We felt that that at least gave us the enough antennas to create a problem if one did exist. And the antennas were, I think some of these are prototype antennas. They were positioned in the yard at the NOAA facility in the same relative position that they would be placed when they're on the Ogee. And the results were good. So testing, so the synchronization algorithm that was developed was effective. And another test that we conducted was to place the antenna in water and then put concrete blocks that match the same composition as the concrete that would be used at the actual install on the antennas. We wanted to, there's this big discussion on how little is it non-magnetic sand or non-magnetic cement that goes into the composition. So there was great concern or uncertainty. So to get rid of the uncertainty, we tested it. So initially we tested with blocks. So here's a painted aluminum shield. You can see the antenna underneath, and then the concrete blocks. And we did see some issues there, and we thought that they may have been related. And this thing creates 30 amps. If you get too close to the shield, you may get shocked. So it's creating a tremendous amount of power, the antenna is, and we were thinking that the gaps between the blocks might be the reason for some of the static that we saw. And so the next test was to just entomb the antenna in the same concrete composition, but completely entomb it in a monolith, flood it. We have the same stainless steel conduit that was going to be used. So this represented, as far as we could get, the configuration that would be used at the installation. And then once all the antennas, the transceivers, the power supplies were tested in Boise at Biomark's facility. They were tested in the Pasco facility in Washington, and then transported about approximately 2 hours to Lower Granite Dam, where everything was tested again to make sure nothing broke during transport, and also that the final location was acceptable with respect to electromagnetic interference, which it was. And then finally, the antennas were installed on the Ogee. So here you can see the 3 rows, the 11 antennas. Each antenna had two stainless steel conduits that ran from the antenna up to the transceiver room, which I'll show in a couple of slides to connect to the transceiver. All of the rebar that was replaced or used within the new construction was fiberglass rebar, not ferrous rebar. And then all the antennas, we had a hatch constructed on the antenna, but we also had to have a means to get through the concrete pour. And so hatches were built that sat right above the hatch on the antenna, and to allow us to access the hatches through the hatch once the concrete was poured. And here's a picture of the hatches. So these are all fiberglass frames with fiberglass rods to key into the concrete, and then the UHMW hatch that could be removed to access the capacitors. Here's a picture of the electronics trailer. So again, each of the antennas has a dedicated transceiver. All the transceivers are located in the lower enclosure. We have stainless steel conduit that runs up to the bottom of the enclosure. Here's a picture of the inside of that trailer with all the enclosures and the stainless conduit running up to each enclosure. Gabriel giving a tour. And then the upper connex trailer, or the penthouse, holds a couple of computers that are used to collect data locally and access points for remote communication. Here's a close-up of one of the electronic enclosures. So a power supply that Alex Archikoff assembled that allows providing 50 volts DC to the transceiver. Here are the guts of the transceiver. And I guess that one of the unique things about the transceiver is each of the processes, the detector, the exciter, the CPU, are contained in separate modules, and each of those is shielded independently from each other to reduce the amount of interaction, just to the highest level possible. Additionally, each of the enclosures contained a fixed value capacitor here, and then also an air variable capacitor on the transceiver side. So we had tuning transceivers, we had tuning capacitors on the antenna, and then a tuning capacitor in the enclosure that allowed us to make some fine scale adjustments to the tuning circuitry. It cost about $30,000 to mobilize the construction crew to provide us access to the Ogee surface. So if we were able to make changes without doing that, it was a huge time and cost savings. So the antennas are in, and now it's time to pour concrete. You can see all of the white sticks or fiberglass rebar. Here's the construction crew. By this point, we've finished the pouring on the south side, and then the crew there's a pumper truck that's behind me when I took the photo. Here's the hose from the pumper truck providing concrete. These guys are, a matter of, they're doing concrete work. You have 3 or 4 guys in there with vibrators or stingers, making sure the concrete flows down into all the interstitial spaces. And there's a roller to help smooth that surface. Here's, let's go back to that. This is a video of that process. You can see the scree roller. It's 2 continuous pours, one for each side of each side. They used 100 cubic yards, or something like 100 metric yards of concrete. They poured one side and then poured the other side. And it was really impressive. I mean, every single load that came from the batch plant had to be was tested. And these guys just did a phenomenal job. Here you can see the top of the hatch that was later accessed. So let's go here. And so here's the final product. This is right as the north side was just getting done. At the south side and the north side. And then finally the concrete cured for a couple weeks, excuse me. And then Gabriel went back, and Gabriel and the guys from Pacific States went back to conduct the measurements. So here's Gabriel. So there were, now that the antennas are covered up, you can't really see them. So the construction, I guess I'm not entirely sure. The construction crew, I think, put lines across the middle of each row of antennas that would provide a reference for the guys taking measurements. And here's Gabriel tethered off, and then I think Scott Livingston from the Pacific States Marine Commission, and used an FDX-B tag, our APT12 FDX-B tag, to measure read range at 12-inch intervals across the Ogee surface. So it's a pretty exciting location. I think it's a 1-to-1 slope that they were working on. Excuse me. And this all, ultimately it confirmed the read range that we saw during the development phase. And here's another plot put together by Gabriel. So this is kind of an end view. If you stacked up, there are 11 shapes here, and if you superimpose them on top of each other, this is what you get. The key things to point out are this blue dash line is the blue dash line, which is 24 inches above the surface of the concrete, and really where we thought the majority of the fish would be passing below, kind of in the water that I guess I call it solid water, where it's not foam or spray. I mean, that is where the fish are going to pass. And you can see that, within this area or volume, the vast majority of paths indicate two or three antennas or detection opportunities. So it's really encouraging. They did some test measurements with tags embedded in sticks, and due to the water velocity, initially the sticks were being launched out of the spray until they weighted the sticks down with rocks, and that helped them at least stay submerged. There was a live fish test was planned for April, but it was canceled due to the COVID pandemic. And then finally,
question for you.
Yeah.
I think you kind of touched on it briefly, but another tag question. You had mentioned most of the testing was done with the standard FDX-B tag. Can you explain that a little further?
Yeah, so that all of the tags we use this is really developed around FDX-B tags. The FDX-B tags are on continuously. When it's energized, when it passes into the field and it's energized, it's communicating continuously with the antenna or the transceiver, back in the reader, as opposed to a half duplex tag where there's two phases. There's the energization phase, which is, as an ISO standard, is 50 milliseconds in duration. And then there's the quiescent phase, a 20 millisecond, and that's when the tag transmits its signal. In this location, as well as all the juvenile bypass systems in the Columbia River Basin, the water velocity is so fast that you would miss half duplex tag just to the pure operation of the tag, this 50 to 20 cycle. I mean, you have to be in the field long enough to get energized, so you have to be in there for at least 50 milliseconds. And then you need to stay in the field for another 20 milliseconds in order to transmit its tag signal. So half duplex tags are out for this high-speed type of application, and really, so the FDX-B tags are used predominantly in the Columbia River Basin, and it's really the only tag that will work in this scenario. And so we were greatly relieved, and I'll get to the punchline here in a little bit, that the standard FDX-B tag, Biomark APT12 or HPT12 performed very well. And then the half telegram tag in the static testing performed well. And Gabriel and the other regional managers could probably speak more to the need for an APT or more to the need for a fast tag or half telegram tag. But it seems like the standard telegram tag was very effective, provides enough effectiveness where that the faster tag may not be required for this application.
Okay, great, thank you.
Here's a final picture taken by Joe Norton from the Corps of Engineers. You can see the hatches, nice smooth concrete surface, and the access hatches to each of the antennas. Access the capacitor compartments of each of the antennas. The final shot of the Ogee once it was open. So again, a very dynamic environment. Fast water, huge project. The Corps of Engineer was great to work with. Their contractor was great to work with, and BPA. So it was a huge collaborative effort. So ultimately, the reason for the spillway detection system was to be able to supplement detections at the dam that were being lost due to water going through spill or fish going through spill. So as of yesterday, there were almost 157,000 unique tags detected on the Ogee system, the system here, and that's from, I think, the middle of April until June 22nd, compared to 34.5 thousand or 34,549 tags detected through the bypass system. So prior, without the Ogee system, without the Spillway Ogee system, they would have relied on this 34,000 tags to, help guide the SAR. But now they have the additional 157,000 tags that were detected just on this location, just on the antennas or the Ogee system that we installed. So it was a huge success from that aspect. And the other interesting aspect is it was put in to determine, smolt to adult return rates or SAR, but it's which you have to wait for the adults to return, which could be 3 to 5 years depending on the fish species, and run. And it's providing information right now just on how to manage flow and run timing of fish approaching the dam, and so it's providing information now that wasn't anticipated, right? I don't believe that it was anticipated. So that's certainly a cool aspect. So this did not happen alone. This is a list of, kind of the key individuals from the main organizations from the BPA and the Army Corps of Engineers. And as again, a hugely collaborative, successful project. And as far as I'm aware, it's the world's largest pit tag detection system that's currently operational. With that, I would be happy to answer any questions.
Thanks, Steve. Nice job. Pretty cool project. We did have a couple more here for you. One of the couple people asked this: what are there any plans to replicate this or add other facilities in the Columbia or elsewhere? What's the sense there?
Yeah, I know there's a working group right now that's looking at options for enhancing pit tag detection at Bonneville Dam. Currently, there's an antenna in what's called the corner collector at Bonneville Dam. It's a 16-foot by 16-foot antenna, so it's very large. And a lot of the transceiver that was used on the Ogee project is related to the transceiver down there. And so looking at the cost benefit, again, Bonneville Dam's the last dam. Do we add another corner collector antenna? Do we add an antenna to the ice and trash sluiceway at Bonneville? Do we add an antenna to the spillway? So I think, given that, budget cycles and everything else going on, that is the current conversation that's being had. There are other RSWs in the Lower Snake River, but I think the effort at Bonneville Dam would be the next thing to happen. And then that being said, that could be 3 or 4 years from now, but that's the one on the table right now.
Okay, thank you. And then kind of along those lines, was there anything that we learned during this process that could be applied to just future pit tag systems in general, not necessarily something of this scope and scale?
Yeah, I mean, there was, the use of ferrite tiles. We've implemented that into some of our what we call a low profile antenna, where we can build, and usually traditionally you might need say 6 to 10 inches of separation between a coil and ferrous metal. This allows us to reduce that to 2 inches, so we can have an antenna that's 2 1/8 inches thick and place it right next to steel. So that was a huge advancement. Use of Litz wire we continue to use in the large majority of our antennas. And then the improvements in the tag detection algorithm that's been implemented, and some of the logic is fed into our standard IS-1001 reader that's used, we use for the vast majority of the systems. And I guess from a larger, kind of not specific advancements, but we push the group pushed the envelope of what could be done so far out there beyond what is traditionally done with fishways and in stream, that there are a whole bunch of opportunities between what we did here and where we are. So the envelope is so far out there now, when a project comes up, like, yeah, we could probably do that. Just because this is so far beyond what anybody suspected we could do. And full disclosure, we were all greatly relieved when it worked. So it was very rewarding.
Okay, great, thanks. And then another question. Somebody, I think they missed it during the presentation, but they wanted you to revisit the profile of the antennas, how tall or how high they were. How tall, how high, the thickness, I think is what they're getting at there.
Final ones?
Yeah, and I'm not quite sure if it's the read range they're looking for or the actual, physical height of the antenna. Maybe you could just reiterate both quickly.
Yeah, so the flat plate antenna was 12 inches tall. So the final antenna was 12 inches tall, 8.5 feet by 4 feet or 8 feet by 4 feet by 1 foot tall. And I can provide, you know, that information as well.
Okay,
Is that the answer?
Yeah, I think that answered it. Okay, I think we have made it through all the questions. Steve, thanks again. Great job.
Okay.
Just to reiterate to everybody, this has been recorded. You will receive a link, and we'll get it on our website. We'll get it on social media, so feel free to have a look at it, reshare it, whatever. And we are here, so please contact us if you have questions, you know, further comments, that sort of thing. And thanks again for everybody for taking time to join us today.
Thank you, everyone.